All right, let's take a look at this. I'm going to make sure everybody knows what's due this week. Under week 4, remember to do the discussion. You can see people already started that. So discussion for week 4. Under wiki project, so let's come over here. What you're going to do this week is you're going to summarize the results of your study that you have. Okay? So you've done the introduction, you've introduced the paper. Now tell us what they found. Okay? So it says here, what did the study find? Does this seem valid? So think about whenever you're reading any journal article, you need to really look at it with like a critical eye, you know? Just because something is chiropractic doesn't mean it's actually a good article. It could be terrible. And that goes with any study and, you know, any field. All right? So look at it with a critical eye. Be as critical as possible. That's better. Because once you realize the flaws, if there are any, then you know kind of how much weight you could put into this paper. So look at it. You know, for example, usually you want to see, you know, quite a few people participating in the study. The ideal number is usually around 30. You can't always do that in chiropractic, but if you can get up to 30, that's pretty good. Anyway, so if they do this study, for example, on one person, and then they try to generalize to everybody in the world, okay? Now, if it worked for that one person, great, but it doesn't necessarily mean it's going to work for everybody else. Not necessarily. It could, but you don't know. That's the thing. You don't know. So watch what sort of like conclusions they're trying to make. See if they're leaping, you know. Also look at if there's anything else that could explain the behavior or the, you know, the results that they saw. Okay. I'm trying to think of something. Maybe, you know, doing 2 adjustments a week, they lost 10 pounds in a week. I don't know. Okay? But maybe they didn't talk about their diet at all. All right? So maybe actually what was happening, maybe the adjustments help, and maybe they're actually, you know, eating completely different. Okay? But they never talked about once what the people were eating, if it changed. All right? So just stuff like that. Just see if anything else could explain it. Do you see any flaws? If you did this study yourself, how would you do it differently? Would you use a different type of people? You know, like maybe one of them has athletes, so maybe you would do this study with non-athletes and see if you see the same results. Or maybe there's a huge flaw. Maybe they're not controlling for diet or something like that. So you would do it again by saying, this is the diet you will eat every day to make sure everybody's the same, or something like that. I don't know. So how would you change it? How would you do it different? How could you apply this to your own practice, like to your chiropractic career? Is this useful? Maybe it's not. Maybe you find it's actually, once you look at it, it's a horrible study, and it's really not going to apply to your practice until they do more research on it or something, okay? I don't know. So let me know how you could possibly apply it to your practice, why or why not, you know, to your career. Also, look at your comments that the other groups made and adjust everything from there. So don't delete the comments. If you do by accident, it's not the end of the world. But try not to delete them. Just read them and then change what they said if you agree with it. If you don't agree with it, you might comment right below it and say, you know, I think this is fine because X, Y, Z. Okay? So just because they made a suggestion doesn't mean you have to necessarily do it. Okay? So change it, make it look really nice, and then I will, at the end of the week or next Tuesday or whatever, I will look at your wiki page again. So at that point, by next Tuesday, you'll have to have looked over all the comments the other groups have made, you know, edit those as you see fit, and summarize the results, you know, look at the study and apply it to your own practice. Okay? So that's wiki. Sapling, homework 4. Homework 3 is due tomorrow. at midnight, and homework 4 is due Monday at midnight. And then also I want to show you the lab. Okay, remember the labs always have the vodkas, so if you get stuck on anything, those could possibly help you. Maybe, maybe not. Lab 6 goes over radical reactions like we've been doing, you know, the initiation, propagation, termination. So the first part of the lab, look at these. This is the pH numbers here. So this is a mock study, if you want. And look at where on here would probably be initiation. So what is initiation? It's the beginning, right? So it would probably be where? At the beginning, maybe the first reading, okay? And then propagation, what's happening in propagation? Everything's reacting, you're forming your products kind of thing. So look at where it's reacting, where it's changing. And then termination means it stopped, you know, it finished, okay? So look where, see where it looks like it finished, okay? So that's where you're going to kind of read the results there. Here you're just writing out the mechanism. This is one of the energy diagrams. On this one, it goes forwards and backwards. So sometimes it says, you see this says A, B, C, D. So sometimes it says to look at it, A, B as your reactants, C, D as your products. And sometimes it's C, D as your reactants, A, B as your products. So they're looking kind of back and forth there. And then the last part is using models to make cyclohexane and doing the cis and trans axial equatorial and doing that stuff. And over here, this is your rate. I know some of you already started this. So this is, you know, you're looking at the molarity of these. So remember, we're looking at when we double the molarity, hold one of them constant, double the molarity of one of them, what happens to the rate? And you literally just time it. Now this here, see where it says so right here, these are in seconds, which is just literally time it in seconds. And then over here, do you see the rate is actually in seconds to the -1? What does that mean? 1 over seconds. Okay, so whatever your average number is here, divide that 1 over that number is what you have for your reaction right there. And you do that twice, and then answer some questions. Okay? So that's what this week's lab goes over. Here it talks about what you want in the video. Video 1 or lab 6, you want to include you working out number 2 mechanisms. Look at the question number 2 on there and just kind of show me how you would work it out. And then show one of the ring flips. So show me your model kit and how the ring flip, kind of explain one of them. Here on the video include part of the experiment when adding the chemicals. So show me one of your trials where you're timing it, okay? And then show me how you derived your rate law. So if you're saying it's first order, second order, show me why you think it's that, okay? So that's it for the lab. We're like halfway through with organic 1, so it's just weird. And that is all that is due for this week. Okay, any last minute questions about the exam? About any of the content or anything? You understand everything? Okay. No, there's no partners this time. This time you're going to do it by yourself. Evidently the microphone didn't like that. So be sure to study it like you're doing it by yourself. And what I think I'll do is whenever I'm done grading them, I've gotten permission to hand them back just for the day. And then what we'll do is we'll correct them in partners. Okay? So that's this week. So you're taking it by yourself this time. Any other questions? It's the same exact format. So the first half is multiple choice. The second half is workout. Be sure you read everything on there, especially like the workout, because I might say, do this, this, and this. So make sure you do everything it says. So read, the question very carefully. And for the multiple choice, I would recommend kind of working it out as a workout and then pick your answer. I found that when the students do that, they do a lot better on it than going backwards, looking at the answer, and trying to figure out from there. So, cover up the answers, work it out for yourself, and then whichever one matches up, you have it. Assuming one of them matches up, you have a good chance that's actually the answer. So, any other questions? There's 20 questions long. There's a bonus at the end, so be sure to do that. The periodic table is on there, like last time. Bring a Scantron for the multiple choice. Anything else? If you think of anything later, just email me. Okay? All right. So let's look at this. What I wanted to do is to start off just working out some problems with Chapter 5. Yes? Uh-huh. Like the answer key, like I call it? Yeah. Okay, yeah, let me do that really quick. Do you want me to do both ring flips or just one of them? Okay. And I'm going to put A and E for axial equatorial, okay? So again, notice they alternate. So that one's up, down, up, down, up, down. And then equatorial, I'll draw on here. But if that axial is up, then on that same carbon, the equatorial is down. So I'll draw that in blue. There you go. And so at the A's and the E's, you could put hydrogens, methyls, ethyls, whatever there. Uh-huh. So I'm going to keep the colors the same. So you see how this was a red axial? Now it's going to be a red what? What is it? Equatorial. There you go. So when we do a ring flip, does the direction change up and down of the branches? No. But what does change? Axial and equatorial. All right, so let's work out some problems. from chapter 5. These are anywhere, just so you know. Here you go. There's some of them. Hold on. Cover that part. So basically for all three of those, you can work in groups. Tell me if they're R or S. So you'll have to find the stereocenter or the chiral carbon. Now, what's a chiral carbon? How many different groups does it have coming off of it? 4. And also give you a hint. Only single bonded carbons, like sp3 carbons, can be chiral. Because when you have a double bond, then you only have 3 things coming off. All right, let's start looking at these. So the first one, let's do the priorities. So this is ibuprofen. Where's your stereocenter? Yeah, it's always the carbon that shows the wedges and the dashes. So here, what's priority 4? Hydrogen. Which one's priority 1? This carbon, oxygen. Priority 2, the ring. And then 3, CH3. Okay, is our priority 4 already back on a dash? Yes, so it's going to be exactly how we see it. So we see 1, 2, 3. What is that? Counterclockwise, so that is S. So is this the active ingredient? Yes, so this is the active ingredient of ibuprofen. The R is actually just completely inactive. Oh, well, that is the full one for one. I mean, the only thing, there's a carbon there. So it's carbon connected to oxygens, and then this here, carbon, carbon, hydrogen, carbon, hydrogen, carbon, carbon, hydrogen. So there's, you see this is connected to, directly connected to a carbon, and that carbon is connected to carbon, carbon. And then this carbon here is connected to oxygen, oxygen. So it would have a higher priority than the ring. It'll trump it, yeah. You just go one atom at a time. Don't look at the whole thing. It has a higher atomic number on the periodic table. Basically, it weighs more. So again, you're first going to look at carbon versus carbon. That didn't help us. Those atoms are the same. So then look at what those carbons are connected to. Carbon, carbon, oxygen, oxygen. Oxygen is a higher atomic number than another carbon, so it wins. What about this one here? This is the leave. Let's see. Over here. So what's priority 4? Hydrogen. 3. Methyl. And then here? The what? The ring. And then 1. CO2H. The CO2H is this right here. Do you see that it's actually the same 4 groups coming off of there? See, we had hydrogen, methyl, ring. The rings are different, but still a ring. And then C, do you see O2H? CO2H. Do you know what drug classification ibuprofen and Aleve are in? NSAID. They're both NSAIDs, so that's why their structures are similar. Okay, so let's look at this. Is our number 4 priority going back? No, so we're going to have to change it. So what does it look like? We have 1, 2, 3. So it looks S, so it's R. So for this one here, for Aleve, S is the active. R is actually a liver toxin. So what did we just take? So this one's active, and this is a liver toxin. So what do we take? The liver toxin. Now let's look at what we're going to eat down here. Poison or no poison? Okay, so this is the stereocenter here. What's priority 4? H. And then what's priority 1? Nitrogen. And this is where the harder part comes in. So here, what is that? It's a CH2, right? CH2, and then over here I have a CH2, so that didn't help. Let's go to the next one. I have a CH2 again, and a CH2. That doesn't help. Let's go to the next one. CH2 and CH2. Again, that doesn't help. CH2 and a CH3. What would be a higher priority there? CH2. Usually the less hydrogens, the higher the priority. So this ring over here is 2, and then this one is 3. Does that make sense how I did that? So you just keep going around until they're different. So now knowing that, what do you get? Yeah, so it looks R, so it's actually S. So did we kill ourselves? No. So these are harder. These are, actually, do you see how these compounds can get really huge? So these are larger. Usually we've been practicing with something like this. Okay, so these are a lot harder. So if you can get these, I know they were difficult and you probably had to work a little bit at them, but if you can get these, then you could feel pretty confident. Yes? Why is it S? Because you see my hydrogen is on a, or I shouldn't say hydrogen, my number 4 is on a dash. So I don't have to change what I see. But do you see over here it's on a wedge? Then I have to change what it appears. So the only, dash will always stay the same, or what it appears is what it'll be. And everything else will change. It'll be the opposite. Correct. Okay, I also wanted to show you that, you confront these all the time in nature. This is hemlock, which is it's a plant. And then ibuprofen and a leaf. And I think it's next week. You'll read a paper. It's pretty interesting. It talks about enantiomers, R and S. And it gives a list of a lot of the different drugs out there that have R and S enantiomers. Which one do they actually take the time to separate them? Which ones do they keep the same? Anyway, so you can have a whole list of those drugs currently on the market. Okay, so I did want to show you. Hopefully it's on there somewhere. Let me see if it's here. Here. So this was under week 4. Do you see where it says chapter 5 notes? These are some of my handwritten notes. If you can't read them, I'm sorry. But it'll help define a lot of the things we're going to go over. The hardest part about this chapter is understanding the vocabulary. Okay? So once you get that down, the chapter is not too bad. Okay, so here's just a list of some of the vocabulary and a couple of examples there. So you could print those off and see them. It's basically this chapter summarized into 2 pages. Okay, this is how I always studied organic chemistry. I would look at my notes and summarize them in a page or 2. What are the biggest points? And it really helped, especially when I was studying for the final. So I didn't have to go back and read all my notes again. I had these summaries of every chapter in a page or 2, and it saved me hours of studying. Anyway, so that's to help you, and that's under week 4. Here's this chapter 5 notes. Okay. Okay, what is an enantiomer? Okay, so we'll think about this. Does an enantiomer, is it a relationship, or can you just say one molecule is an enantiomer? It's a relationship, so it's between 2. Do you have to have a chiral center? Yes, so you're looking at two things with a chiral center, and the other thing, the requirement, is they're mirror images, so they're opposite of each other. So if one is an R, the other one would be a S. And do you remember how to go back and forth between enantiomers just really quick? Like, you what? Yeah, you flip two bonds. So, and I usually just flip what's on my wedge and the dash. So draw everything exactly the same, except whatever was on your wedge, now draw it on your dash, and whatever's on your dash, draw on your wedge. So you just switch those. Properties. So remember, they have the same boiling point, melting point, density, etc. So all their physical properties are the same. So they're really hard to separate them in the lab. Okay, but remember, they rotate polarized light different. And then also other enzymes and receptor sites can tell the difference. So the enzymes in our body, our nose, remember some things will smell different. How we taste them will all be different. So we can tell the difference, our body can, I should say, but in the lab, we really cannot, okay, unless we have a plain polarized lens. A polarimeter is what it's called. Okay? All right, so here's an example of a polarimeter. Now remember, when I have my enantiomers, so I have my R and my S, okay? Remember the R, if we have our plain polarized light, so this is showing you, here's my light source, okay? Do you see that it goes through, it's trying to show you all the different angles here, so it's pointing in all different directions. Then I go through my polarized filter, so it's only going to let in one direction of light go through. So do you see the direction, this one's letting it through, the slits are going up and down? So then what's going through? Just the light that's pointing up or down. Okay, so only one direction there is showing, you know, going like that. Now, here's my sample cell. So I filter my light, so I only have one direction going through. Okay? Now this, let's say this has my R in there. Okay? Now do you see what happens? Now right here, before it's actually passed through it, the light's going up and down. But as it goes all the way through the sample, what's happening to these arrows? Do you see it's twisting a little bit? Okay? And what it does, it rotates that light to a certain degree. And then here's where you can analyze it, and you can actually look at the light and see where it's rotating to. And so each enantiomer, so each molecule has a unique angle that it rotates to. Okay? So if you did ibuprofen, I don't know the angle, but let's just say it's 30. Okay? If you did this, it'll always rotate the light 30 degrees. Okay? And there's a reference, an index you can look up to get all the different rotations and everything. The other thing to keep in mind is that R and S have nothing to do with the direction they rotate light. Okay? So when we do R, we think clockwise. When we do S, we say counterclockwise. Okay? Those are just our own rules in our head to decide if something's R or S. Now, experimentally, to determine how it actually rotates light, that could be different. So R could rotate counterclockwise or clockwise. It just depends. So that's something only experimentally can you determine that. So how we do it, which is called the pre-log rules, where we set the priorities and we look, okay, are the priorities going clockwise or counterclockwise? That's one thing. So put that kind of in a little box. And then another little box of ideas is how it actually rotates light. Okay, experimentally, okay, which could be the same, could be different. When we do these, when something is rotating light clockwise, we call it dextrorotatory, where we just say a plus sign, or sometimes we just put D. Counterclockwise is levorotatory, and that's a negative. So when you, let me see if I can find one. So not related to R and S. Okay. So if I show you, here's a name right here. Okay. Here's epinephrine. All right. This has an R. So the R stands for R, like we would have looked at it and decided it was an R. But what does this negative mean there? What, experimentally, how is it rotating light? Counterclockwise. And then we can look, so that one's the S. Notice the S here, so if the R is negative, the S is positive, okay? So it's the same magnitude, so it'll rotate light the same magnitude, just the opposite direction. Here's another one, butanol. S is positive, so which way is it rotating light? Clockwise, and then this one, R, is going to be the counterclockwise. So it's not necessarily that way every time, but anyway, so you can go on, we can look at more of those. But so R and S have nothing to do with how they will rotate light. You have to do the experiment. Okay, but you can look at a name, and it'll always tell you, you know, okay, this is RS, and then also tell you experimentally how it rotates light. Okay, clockwise or counterclockwise. And you see right here, do you see that I have a plus 13.5 for the S, and then for the R is the exact same magnitude except negative. Okay, and that always occurs. So they're the same magnitude, opposite signs. Okay. So let's go ahead and take a break, and then we'll look a little bit more into them. All right, let's go ahead and start back up. Again, remember to bring the attendance back around. Okay, I did want to show you this slide here. Remember I told you that enzymes can tell the difference between enantiomers, between R and S? So here's epinephrine, okay? And this one is the natural one, okay, which means your active one, and it's R. Okay, now let's look at this active site. Now this is kind of a really very crude picture, but it works, okay? Gets the point across. Know that your enzymes are actually made up of huge, giant molecules, okay? But let's pretend they're made up of shapes, okay? So let's look at this. We're going to put epinephrine onto the enzyme. Now just look at the area it fills up. Do you see that this kind of ring here fills up this space pretty nice, and then this nitrogen carbon group, and then OH, okay? Now look down here. Here is the S, which is the unnatural, okay? So this is the one that's inactive, okay? Now the ring is still in the same position, but do you remember, how do we make the enantiomer? How many positions do we switch? 2. So do you see they switched these 2 down here? Now this OH, do you see the OH is kind of too small for this area? And then this carbon-nitrogen group is way too big for this area here. So to show you that this will have no effect. So if you have the S epinephrine, really your enzyme won't even acknowledge it. It won't do anything, okay? But the R epinephrine, it fits into that enzyme site correctly, and you're going to have your effect, your regular effect with epinephrine. So again, to show you, your body can tell the difference between these. Okay, then we get what's called racemic mixtures. This means in a beaker we have equal amounts of R and S. So what ratio would that be? 50-50 or 1-to-1, okay? However you want to say it. It means the same thing, okay? So they're equal amounts. So let's think about this. So here's a 2-butanol, and it rotates light, the S, a positive 13.5. And then here is the R, and it rotates it negative 13.5. Now there's equal amounts of both, okay? So kind of add these numbers together. What do you get? 0, okay? So when these are by themselves, you would see, remember in our polarimeter, it would rotate light clockwise 13.5 degrees. And this one by itself would go counterclockwise, negative 13.5. But whenever you have exactly equal amounts of each, you'll have no rotation of light at all. Okay? You won't see anything. The light will pass through like there's nothing, like just water in there. Okay? And that's called a racemic mixture. And again, that just means you have equal amounts of your R and S, and so it cancels out the rotation of light. There is no rotation of light, or you won't see any. Okay? And we'll go over this another time. I don't think this is an appropriate spot to put it in. But this is just showing you have your R and your S. You have equal amounts, so you'll have a racemic mixture. Okay. Optical purity. Well, you can have different mixtures. It's not always 50-50. So if you have a 50-50 mixture of R and S, you have 0 rotation, so your optical purity is 0. Okay? But what if it's not 50-50? What if it's 60-40 or 75-25? You know, what if it's different? Well, we can still calculate what's called the optical purity. All right? And that basically means which enantiomer, your R or the S, is in excess. And that's why it's called enantiomeric excess. Okay? So let's say I have 60% R and 40% S. Okay? So let me write this down. Let's do this backwards first. So 60% R, 40% S. Okay? Which one is in excess? R. There's more R than there is S. How much more R? What percent? 20%. So this tells us the optical purity of R is 20%. Okay, because let's think back at this. Okay, when we have a 50-50 mixture, it cancels out, right? So do you see that 40% of this, of the S, is going to exactly cancel out 40% of that, right? So 80% essentially is impure because it cancels out, leaving us with the 20%. Do you follow that? So again, if this is 40%, that means it's going to cancel out 40% of that, leaving us with 20. Or another way of saying that, 20% excess. So that's what's pure. So you can go the other way. So that's if I give you numbers. So what if we had this? So here is the formula that you use. The observed rotation. So what do you actually see? Kind of like your actual over theoretical. This would be your actual. What do you actually see? And then rotation of pure enantiomer. So theoretically, if it's pure, what rotations should you see? So they had an example here. Okay, the specific rotation of S2 iodobutane. So specific rotation is of the pure enantiomer. Okay, so it's a pure S2 iodobutane is positive 15.9. So just from there, let's think about what we just learned. First of all, which pure enantiomer are we looking at, the R or the S? The S. Do you see right here? And which way did it rotate light? To the right. It's positive, you see, so we have a positive 15.9. So let's write that much down. So our S, well, I'm going to put above it, pure, is a positive 15.9 degrees. So if you have pure S in a beaker and you put it in a polarimeter, it's going to rotate light clockwise 15.9 degrees. That's what that told you. Okay, but now it says, actually, though, we have a mixture. We want to figure out what that mixture is. So I have a mixture of R and S actually in a beaker, and I have no idea. I just kind of mix them together. I have no idea how much R, how much S there is. Okay? But I put it back in a polarimeter, and I rotated the light, and I got a negative 3.18 as my new angle. Okay? So we'll say mixture equals what? Negative, was it 3.8? 3.1? 1.8. Okay. 3.18. Okay. Can you tell by looking at this which one is going to be in excess? The R or the S? Why the R? The sign. Okay, do you see the S would have come up positive. But what sign did this come up as in our mixture? Negative, which means we have excess R. Okay, so now we plug in our formula. Okay, so our actual, so what our mixture, if you want, is what? 3.18, right? So do 3.18, and theoretically, so the pure should come out as 15.9. And you multiply this by 100. And this gives you optical purity. So when you do that, what do you get? What? 20%. Okay, so this tells me this is 20% pure. Okay? Or another way of saying it, an enantiomeric excess. Okay? So which one is in excess? R. Okay, so how much more R do we have? 20%. So we know this is all from R. Okay, so how much of it is impure or cancels out? 60-40, but before that, the total amount? 80, right? If 20% is pure, 80% is impure, right? So 80%, we'll say impure. All right? Now that's a mixture of R and S. Now out of this, so think again about a racemic mixture. So if 80% is not pure, how much of this 80% is R and how much of that 80% is S? 40-40, right? That's the only way they would cancel each other out, is if they're equal. Okay? So I have 40% R, 40% S. Okay? Now the last step, we're almost done here. So is there any more S we talked about in here from this? No. So their S is 40% in this mixture. And then R, we have 40% here that cancel out. And then how much was in excess? 20, which makes it 60%. So just by putting this unknown solution in the polarimeter, we have no idea how much R and S is. We can measure the new angle it rotates light, and then from there plug it into this formula and see, okay, in this case I have 40% S and 60% R. Let me see if I wrote down another example. Okay, I guess we can technically do this. It doesn't come out as pretty, but it works. So if the angle, okay, so the pure angle let's say is negative 13.5. Of whatever. And let's say the pure is the S. Again. And then the mixture has an angle of negative 9.72. Okay, so which one is going to be in excess on this example? S, because we see S is a pure. This is what we're looking at in an index in a chart, and it's a negative. And then when we do our mixture, it comes up as negative. So that's the S. Okay, now let's do the optical purity. Let's see how much of that S is pure. Okay, so what do? What number goes on top? 9.72. And then 13.5 times 100. What do you get? 72? Okay, so 72% of this is pure. Okay, so how much of it is not pure? What did you say? 28? Okay, so out of that 28%, how much of that is R, how much is S? 14, right? Okay, so what, let's see, this is S. So what percent of this whole solution is R? 14. So R is 14. And then what percent of this is S? 86. So that solution was 86% S, 14% R. And after you subtract them, you can see it's 72% pure. Okay, so it's actually a pretty neat little experiment you can do. So if you have no idea, the amounts of each, enantiomer are in solution, you have no idea, just put it in a polarimeter, measure the new angle, and just really quick you can calculate it. Just like that. You can know what percent is R, what percent is S. Because by physical means, can we tell the difference? If we try to do a boiling point or melting point or anything like that? No. There's no other. If I try to do a melting point of a 40-60 solution and a melting point of a 75-25% solution, it'd be the same. You wouldn't be able to tell the difference. But with a polarimeter, you can, and you can actually calculate the percentages of those. Really quick with this, so the chirality of like a cyclohexane here. So when we do cyclohexanes, do we have them ring flip? Right? They can ring flip. So pretty much what they decided is that even though one ring flip might be preferred over the other, for the most part they're pretty close to 50-50 of how they exist. Okay? They'll flip back and forth pretty quick. So if I had this and it flips back and forth 50-50, so 50% of the time it's this, 50% of the time is that, does it kind of sound like a racemic mixture? Yeah, so a lot of times cyclohexane, even if it does have a chiral center, it won't actually be optically active, meaning that it's inactive because it cancels itself out because it's a racemic mixture. The exception, even if it's pretty close, you'll see that. Now look at these rings here. So it's kind of like a ring on a ring. So let's pretend one of the rings was a branch. You see that this branch is really large? Okay, so whenever you get really, really large branches coming off your rings, then they're not going to ring flip. Then one is definitely favored over the other. Kind of like when we have like an ethyl versus a methyl. Which one prefers to be equatorial? Ethyl. Now, in all honesty, the difference between it is not that huge. But let's say we have this huge branch, that's 20 carbons long coming off of there. Then that one for sure has to be equatorial, right? And it's so big that it won't even ring flip back to the other one. Okay, so the larger your branch is, the more likely you won't be able to ring flip at all. And so that will be optically active. Fisher projections. In biochemistry, you'll see some molecules like this with the wedges and dashes, but a lot of times you're going to see them like this. You see it kind of looks like a cross there, or a T. Okay? Those are called Fisher projections. So we've done Newman. Remember, Newman is with the dot and the circle, and you rotate those. Fisher always looks like a cross-section here. Now what they do with the Fisher, let me show you this model. So here's one of the models we were working with yesterday. So, I know, something like this. So here is a regular conformation we see. And with Fisher, all they do is they grab this and flatten it. Okay? So all I do, you see my white one, the one that was going back, okay, is now going kind of forward. So do you see these? Do you see these are pointing down? And then these are pointing up, okay? So whenever you do a fissure, since these are up, these are going towards you, they're always on a wedge. So everything going left and right on a fissure is always a wedge, and anything going up and down is always on a dash, okay? Now, do you see when they draw this, do they draw the wedge and dash in there? No, it's just implied. You're supposed to just know that it's always like that, okay? So knowing this, let me redraw this. So I have, I'll flip it over in just a second. CH2OH, OH, CH3H. Okay, now going left and right, what do I have? Wedge or dash? Wedge. And up and down is dash, okay? Now tell me if this is R or S, knowing that. So I have wedge, dash. So it's always implied, okay? They don't necessarily draw those in there. Okay, so let's look at it. So what is the first priority? Or let's say number 4, I mean. H, right? And what would be number 1? OH. So between CH3 and CH2OH, what would be number 2? The top one. And this would be 3. Okay? Now, is our number 4 priority going back? No. So what does that mean? It's going to be opposite. So it looks like 1, 2, 3. It looks counterclockwise, which would be S. So it's actually R. And what you're going to find with all fissure projections is always going to be opposite what it looks. You're always going to change it because they always, unless they're trying to trick you, and sometimes they do that in textbooks, but if you actually do a true fissure projection, your hydrogen or your number 4 is always on a wedge. So you do the same rules. These don't change. So you do your priorities the same, and you'll find that your number 4 is always on a wedge, so you just change what you see. So it doesn't change any of the rules. You're going to label these the same. It's just another way of representing molecules. They represent sugars a lot this way, your carbohydrates. These cross sections like this. Of course, they're a lot bigger. They're going to look, let me see if I have a bigger one. Well, this is a little bit bigger. You see, now I have 2 cross sections. Okay, so then how many chiral centers? 2. It's usually 2. Sometimes, again, they'll trick you. But yes, there are 2 here. Okay, so let me go back. Fissure, okay. No, that's just showing you again. Rules with these. Do not rotate these 90 degrees. So you know how with a Newman projection we can rotate them and kind of see the energy involved with rotation? With these, it's not a simple rotation, so you can't just in your head try to rotate this to there and this to here. Like, they don't rotate 90 degrees. But they can rotate 180 degrees. Anyway, long story short, if you're trying to rotate these, and I'll show you when you'll actually want to rotate these, but at this point, if you're trying to kind of rotate it kind of like a Newman, don't. Okay? Convert it to a Newman to do it. Okay, so this is just showing you can rotate these 180 degrees. So look at the top and the bottom here. Do you see COOH is on the top, methyl on the bottom? Now rotate 180 degrees. CH3 is on the top, COH is on the bottom. You see these switch positions. So 180 degrees is fine, but not 90 degrees. So don't just rotate, you see this to here, here to here, here, like a fan. You can't actually do that rotation. It's an improper rotation. Let me see if I can kind of show you. So here's my fissure. Do you see how it kind of looks like a cross section when I flatten it down like that? That's how you're looking at it. And I can't, when I rotate these, I can't explain it. They don't rotate like this, anyway, how you're trying to do it, this will not just rotate here and this goes here and there. Anyway, they don't rotate 90 degrees. It's hard to show you on that. Okay, but just believe me. Okay, so what's nice with these, it makes it really easy to draw an enantiomer. Okay, so if I have wedges and dashes, how do I draw the enantiomer? What do I change? If I'm drawing the enantiomer, and I show you like wedges and dashes, I change what's on the wedge and the dash. With these, I just draw the mirror image of it. So let's do two things. First, let's label these as RS, and then let's draw the enantiomer. So let me draw this. You can start working on that. There you go. Now let me kind of show you how to look at this. So do you see this cross section right here, this point? That is where your chiral carbon is, right here. That's a carbon. Now let's see what's coming off of that carbon. Do you see hydrogen would be priority 4? Okay. Chlorine will be number 1. Now let's look at here. Directly coming off here, I have a CH3. And then do you see that if I follow the line, I stop there at my other carbon. Now what's coming off of this carbon? Cl, hydrogen, CH3. So between this carbon, this red one here, and the CH3, which one do you think will be a higher priority? The bottom one. So it's 2, 3. Now 2 is everything down here. All right, are we going to have to change what we see? Yes, you always will with these. So I have 1, 2, 3. What does that look like? It looks clockwise, so it's, yeah, it's not R if we're changing it to S. So let's look at this bottom one. Let me use green, I guess. What would be number 4? H. What's number 1? Cl. 2. That carbon coming up here again. I'm going to now make it green. And then that would be 3. So what do we see here? We have 1, 2, 3. That looks clockwise, but it's actually, it looks R, so it's S. Okay, so let me redraw this really quick. So let's just theorize, if that is SS, what do you think the enantiomer will be? RR. Okay, so this is just the same thing, just redrawn. Now let me show you how to draw the enantiomer. I can say on the exam, here's the original, draw the enantiomer of it. This is how you do it. So draw everything going up and down the same. So I have my CH3, put my cross sections in there, CH3. Now what is an enantiomer? It's a mirror image. Okay, so if I put my plane right here, if this is a mirror image, it's reflecting itself, what would come off right here? Cl. These will match up. And then right here, H. Okay, so if chlorine's on this side, then what's over here? Hydrogen. Just look at what's coming off here. So this carbon has hydrogen, chlorine. I put chlorine there, so hydrogen's on the other side. I have H on this side, so what's on this side? Cl. So do you see it's just the exact reflection? Okay? Now you can label these if you want, but this will end up being R, R. Because how many did we change on each stereocenter? 2, right? We kept everything going up and down the same, and we just switched those 2 there. You can see it. What direction is hydrogen pointing right here? Left or right? Left. And what position is it pointing over here? Right? So do you see that we actually switched the direction it was pointing in? So in doing that, when we switched 2 like that, we changed the stereocenter there. All right, then one last thing I want to go over. Diastereomers. So I just, at this point, want to define them. Okay? On this slide here, these are enantiomers. So let's look at this. Do you see it says at carbon 2, we have what enantiomer? S, right? And then at carbon 3, we have which one? R. So this one is a SR. Now the other one here, so this is an S. If it's 2S, then over here it must be a 2R. This one's 3R, so over here it has to be 3S. Okay? So those are enantiomers, and we can look over here. We have an SS, so the enantiomer would end up being RR. Okay? So enantiomers are always completely different. They're complete opposites of each other. Now this is going to be the worst definition of a diastereomer, but I promise this is actually how they define it even in the book. If it's not a complete reflection, then it's a diastereomer. So basically, if it's not an enantiomer, then it's a diastereomer. So let's look at this. They say between here, they're diastereomers. So here I have RS. So the enantiomer would be SR, right? If I have RS, the opposite would be SR. Okay? The diastereomer, do you see, I have 2R, 3S. Now over here I have 2S, 3S. Okay? So did the 2 change? I went from 2R to 2S. Did that one change? So that reflected. That looks good. Now look at this one. I have 3S, 3S. Did that one change? No, it stayed the same. So with the diastereomer, at least one of them stays the same. With an enantiomer, every single chiral center changes. So if we practice this, if our original is RRS, okay? This, pretend there's a molecule. We looked at the chiral centers, and that's what we got. So what would the enantiomer be? SSR, right? Now there's several options here, but so going back to the original, not looking at the enantiomer. Let's say, what do you want to do here? RSS. Let's check and see if he's smart or not, okay? Let's look. It's all up to this here. So RR, did that change? No, so there's not a reflection here. But over here, RS, did that change? There's a reflection there. SS, did that change? No. So did all of them change? No. Did some of them stay the same? Yes, so it's a diastereomer. So I guess you're okay. What do you think? So there's 3 options really what it could be. Enantiomer, diastereomer, the last one would be identical. Okay? If you started off with RRS, what would identical look like? RRS. The thing with enantiomers, I mean, they have all the same physical properties. Okay? Melting point, boiling point, everything's the same. Diastereomers, actually, if we go back here, let's look at these. So enantiomers, do you see, they have the same groups coming off, right? Bromine, chlorine, okay? But they have the same physical properties. Now let's look at just between these two here. Okay, these are two diastereomers. Do you see that they both still have bromines and chlorines? They have the same exact groups coming off. Okay? But let's look at this. Do you see that the bromines and chlorines are both pointing in the same direction here? And then here they're pointing in opposite directions. Okay? Because of that, the difference in electronegativity, so if you're drawing vectors, vector lines, you point towards the most electronegative atom. One line would point towards this bromine, one line would point towards chlorine, so they're opposite. Versus here, do you see they're both the same? So if you were adding vectors, you would get a different number. And because of that, you actually get different properties. So diastereomers, just because the atoms are pointing in different directions, you will get different physical properties. So your boiling points are different, melting points are different, everything's different with these. They're completely different. And it's just by changing that one thing. Because look at here, the enantiomers. Do you see here? They're pointing in the same directions, right? And then here, they're still both pointing in the same direction. Okay, so that's what you're looking at. They're both pointing in the same direction. Okay, so enantiomers, same physical properties. Diastereomers do not. So which one do you think is easier to separate in a lab? Diastereomers for sure. So one way, if we're separating by boiling point, we could do this by distillation. Okay, so let's say, let me just show you this so you can see what I mean by like boiling point separation. You have this flask here. Oh, that's horrible. Okay, here we go. Here's my flask, and here I have my mixture of my diastereomers, okay? Whatever they are. That's my mixture of my two diastereomers. Now what I do, there's a tube that'll pull over here. Actually, no, it'll go down. Okay, let me redraw this. Goes down. Okay. Now right here, so here's my mixture. Right here, I'm going to put a heat source. So I'm going to heat it up to boiling, okay? Let's say diastereomer A boils at 100 degrees Celsius, and diastereomer B boils at 50 degrees Celsius. Okay, do you see the boiling points are completely different? Okay, what do you think I want to set that heat source to approximately? If I want to separate these. What's the lowest boiling point? 50. So what's the lowest temperature I can put this on and have something boil? 50. So usually, we might set it on like 51, 52, just to make sure it gets hot enough. So let's say we set this to 52 degrees Celsius. Okay? Which one's going to boil? B. Is A going to boil at all? No, it's not going to do anything. Okay? B is going to boil, and it's going to collect. So it's going to come here, and then come down here. It's going to start kind of doing its thing. So at boil, what state are you in? Gas, liquid, solid, gas. Okay? So right here, you're going to put, basically it's called ice bath. So we're going to ice. So we're going to make it really cold. Okay? Now, what happens when you have gas and you all of a sudden hit it with something really cold? What will it turn into? A liquid. Think of like condensation on your cup. Okay? So now this is going to come down as liquid. All right? So I boiled off B, and now it's collecting down here, and because of my ice, it turns into a liquid. So after everything is boiled, I watch it, it's no longer boiling anymore, then what have I done? I have A in there, B in here, and I've separated those based off boiling point. Okay? So that's what I mean when one of the big ways we separate molecules is by boiling point. It's through distillation. And that's how it works. Because the boiling points you want them to be at least like 10 degrees difference. Because what if one boils at 51 and one boils at 50? It's so similar, it's not going to separate very well. But if you have, at least like a 10 degrees difference, you could do that. You boil one, leave the other one untouched. and then you can separate them that way. Okay, so diastereomers, you can do this very easily, and anomers, you cannot, because they would both boil at like 50. All right, let's stop there. And remember, your exam is tomorrow, and to bring a Scantron.